Looks like things are working now. Sorry about that. All right, some announcements. Chapter 24 is due on the 27th. I give you the extra time so that you can ask me questions on Monday. I'll be here on Monday to answer questions. Properties of charge is due on the 25th. You should read chapter 24. Next week you should read chapter 25. Okay, that was left over from my Tuesday class. I had mentioned before there's a set of conceptual questions on Canvas for this unit, and you should try to answer those questions on your own. There's a key to it in Canvas, and so that helps you prepare for the exam. There's also a Gauss Law worksheet that's due on the 30th, and you won't be able to start the worksheet until we're done with today's lecture. But before I talk about the lecture, a couple things. Due to a family commitment, I have to be gone. I'm gone tomorrow. In fact, I'll be flying most of the day tomorrow. I'm going to the East Coast. And I'll be gone Friday, and I don't get back until Sunday. You can try emailing me if you have questions. I'll try to get to them as soon as I can. So we won't have the office hours tomorrow, because I think I might still be on the plane. So I wanted to use a little bit of time today to talk about the properties of charge lab. Oh, by the way, Friday you will have lab. Professor Shakel will run the lab, and she's expecting you to ask questions on the multimeter quiz, or how the multimeter works. Okay, so make sure you show up, because if you don't show up, she's going to end the class quick. Okay, because it's really to answer questions regarding that lab. So if nobody shows up, then it will be a really short class. Okay, so go ahead and ask questions on the multimeter quiz. But right now, do you have any questions regarding the properties of charge lab? Or concerns? It's due on the 25th. And granted, the instructions on it are pretty straightforward. Remember that the lab is, you can have partners, but your partners have to be involved in each part of the lab. Okay. Don't expect that this lab can be done at the last minute. Okay, let's see. Yeah, the partner can be from a different section. That's okay. Okay, you can choose a partner from a different section. That's fine. It's just as long as you work on each part together, you're involved in each part of the lab. That's fine. Okay. Are there questions? All right, no other questions? Okay, just remember, on Friday you will have lab. It'll be Professor Shakel, and she's expecting you to ask questions regarding the multimeter quiz. So, you can ask her questions about how the multimeter works, if you have questions about the multimeter, or problems with the simulation that I showed you. Play around with the simulation before Friday. It shouldn't take you that long to play around with it. You'll see how to wire a circuit and make measurements. That's why I give you that simulation, because it's going to help you a lot. Okay. Take advantage of everything that's in the modules. All right. I put that information for you to help you learn the material, so take advantage of the information that's there. All right. Okay, since there's no question, everybody understands you will meet on Friday, and that there's a lab due on Saturday. You all understand that, okay? And you all understand that if you try to work on the lab at the last minute, it's not going to go well. All right, we're going to move on then. Really, my focus today is going to be on Gauss's law. I'm going to finish up the chapter and do some examples. I should be able to finish up the chapter. We shall see. Okay. Remember what Gauss's law looked like. Is this integral of the electric field over a surface, over a closed surface, is equal to the charge enclosed over epsilon naught. And the charge enclosed can be written in a lot of ways. For example, if you're dealing with a charge distribution, it could be written this way. Okay, but it could be written in a number of ways. And I said the other day, if I can pull this out of the integral, I should be able to use Gauss's law to calculate the electric field. This Gauss's law is true no matter what, but it's especially useful if I can pull the E dot n out of the integral sign, because then I can actually calculate electric fields. Now, there is another version of Gauss's law one can talk about. You would have to use something called a divergence theorem to write it down. And I actually have that in your notes, but I'm not talking about it in class. And that version is much more useful than this one. Okay. So I want to do an example of how this describing, what this integral does, what it does for you, how you calculate this integral. And so you see in the slide an example where you have an electric field in some region of space, and I want to calculate the flux, or the net charge, really. I want to figure out what the net charge is through that imaginary surface that you see. It's a box. Okay. The box is 2 by 2 by 2. And none of its corners are at the origin. So let's write down the expression for the electric field. And please stop me and interrupt me if you get stuck anywhere with what I'm saying. Because this is something students will have difficulty with. I've asked a problem like this on an exam before without giving this example, and it caused students a lot of grief. So I want to go over this. All right, so let's say we have an electric field given by the following expression. It's equal to 8I minus 3y squared plus 2j newtons per coulomb. Okay, that's our electric field. In our box that we want to look at, I'm going to try to draw this box up here, okay? I'm not a great artist, so I apologize. I'm going to do it this way. There's my box, okay? And x direction, y direction, and z direction. Okay, let me fix the camera just a little bit. Is it less blurry now?
I think it froze for me.
Yeah, it froze.
It froze? Okay. You can see me now, right? Okay, I can see. All right, so it's not frozen now. So here's our box. This is just an imaginary box I drew. I want to determine the amount of charge that would be in this box if it were real. And I'm going to use Gauss's law to do this. I'm going to integrate this electric field over this box. And really, in this problem, this box has 6 sides. So I'm really going to be integrating over 6 surfaces. If I'm going to do an integral over a closed surface, I got to integrate over 6 sides. So there's 6 integrals I have to do here. Okay, I have to break it up into 6 parts. Now, I want to draw in the normal to each side. So this is the top. This is the bottom. This is the right. And this is the left. And then the hard ones are to draw the front and the back. So there's a normal to the front and a normal to the back. The normal to the front points in a positive z direction. The normal in the back points in the negative z direction. And so I got to take this dot product 6 times. And in fact, I got to calculate the following. I got to do this. And I'm going to need some space. I'm going to get rid of the slide because I need space to write on the board so you can see. Because there's 6 integrals I have to do. I'm going to erase this too, actually, so I have more space. And the area of each side of the box is 2 by 2, so it's 4 square meters. Okay, so I want to calculate all these integrals, so I can get the charge enclosed. So the total, my result is going to be this integral plus this integral plus this integral plus that integral plus that one plus that one. Okay. With some insight, one can realize that you only have to evaluate 2 integrals, okay? With some insight, you can realize that you only have to evaluate 2 integrals. I'll show you why. Let's do these 2. I'm going to do these 2 first, and the reason why is because they're the easiest ones. I want to take the electric field dotted with the normal that points this way. What is that dot product? I'm taking the dot product of this vector with the vector that points in the z hat and the k hat direction. What's that dot product give you?
Zero.
0. So this one's 0. That was easy. Now, what about the backside? The backside points in the minus k hat direction. What's the dot product of minus k hat with this? Should be
0 as well.
0. Okay.
I think because it's orthogonal, right? I can't remember.
Yeah, they're orthogonal, right? Remember, if you're taking the dot product of two unit vectors, like this, one times the cosine of 90, that gives you 0, right? Cosine of 90 is 0. The vectors are perpendicular to each other. The dot product is 0. And so, yeah, you do have to remember the dot product in this course, and also the cross product. Okay, let's do the left and the right side. Okay. Now, if I take the dot product, let's do the right side. The right side points in the I hat direction. If I take the dot product of I hat with this, what do I get? Well, I dot j is 0, and I dot I is 1, and so this is going to give me the one on the left points in the negative I hat direction. Negative I hat times j hat, or dotted j hat, is 0 because they're perpendicular to each other. And so negative I dotted with I is negative 1. I get that. I want to add these two. What am I going to get?
0.
And you know why it's going to be? It has to be 0. Is because this is a constant. Because we talked about the other day the flux through if you have a constant a uniform field, I should say uniform. If you have a uniform field, the integral of the uniform field over a closed surface is going to be 0. And so these two are going to cancel out. Now, these are the ones where that are important to evaluate. And in fact, it's only this term that's important, because this is the non-uniform component. Okay, so let's do the front. I did this twice. Top and bottom. Let's do the top and the bottom. This points in the j hat direction. So j hat dot I hat is 0, but j hat dot j hat is 1 times this stuff. Oh, but what's y across this surface? What's y at the top? Isn't it constant? The answer is yes. So at the top surface, y is equal to 2. So this is really a 2. It's the same value. 2 squared is 4. 4 plus 2 is 6. 6 times 3 is 18. Let's do the bottom. The bottom points in the minus j hat direction. The dot product of minus j hat and I hat is 0. Minus j hat dotted with j hat is negative 1. And then times this thing. But what's y in the xz plane? What's the value of y in the xz plane? It's 0, right? The y-axis is pointing up. Are you guys having a hard time seeing the screen?
It's okay. It's fine.
I'm gonna turn on the auto focusing. Although I don't like that, but see if it makes a difference. Now y is 0 here. So I put 0 here. 3 times 2 is 6. So my integral is going to be this plus this plus this plus this plus that plus that. But the only ones that I'm survive are these two. So I'm going to take the integral of 18 dA minus the integral of 6 dA. And the dA, I mean the areas are going to be the same because they're all going to be 2 by 2s. So it's going to be 18. Oh, I made a mistake. Did you guys find my mistake? I made a mistake here. I don't think anybody caught it. I made a mistake here because I forgot the minus sign here. Okay. The surface area of that one side of the box is 4. I'm sorry, I didn't write the units in. -72 plus 24 is 48 newtons per coulomb meter squared. And that's equal to Q over epsilon naught. And so Q then is, I forgot the minus sign, minus 48 newtons per coulomb meter squared times epsilon naught. So that's how much charge is inside that box. Okay? Let's give you an idea how do you do the integral. I'm sorry, go ahead.
I have a question. How did you get 0 for the bottom?
For the bottom?
Again? Yeah.
Well, the bottom, the normal to the bottom points in the minus k hat direction, right?
Okay. Yeah.
So k hat dot, negative k hat dotted with j hat is 0, right?
Yeah.
And then negative k hat dot I hat is also 0.
Oh, okay. And then, oh wait, so you're doing, okay, so then you got the 2 because you dotted the, wait, how did you get the 2 then again? For the top integral then, above that?
The 2 here?
Yeah.
Well, isn't the top of the box at y equals 2?
Okay, I see.
Okay. The bottom of the box is at y equals 0. It's in the xz plane. Okay. Other questions? Okay, so you should know how to do this problem. It's an important problem that you should know how to do because it helps you to understand Gauss's law somewhat. A little bit better. It's hard to learn it the first time around. You have to see it the second time around, then you get better at it. That's why in physics you'll see this. You'll cover the same topic in the junior level course, although with a little bit more sophisticated mathematical tools. Okay. Any other questions?
Could you explain the dot product again? I'm sorry, I'm just not getting the top and the bottom.
The dot product for the top and the bottom?
Yeah, please.
How do you take a dot product?
You dot 2 vectors with their components.
Okay, let's do I dot j. Are they perpendicular to each other?
Yes.
Okay, so remember that a dot product is the magnitude of the first vector times the magnitude of the second vector. So I'll do it in general. A dotted with B is the magnitude of A, right? This is how you calculate work. And so if the vectors are perpendicular to each other, theta is 90. So the dot product is always going to be 0, if the vectors are perpendicular to each other. So, isn't the z direction perpendicular to these two directions?
Yes.
Okay, so the dot product has to be 0 then.
And then how did you get the 3 and 2 squared plus 2 in your integral if it's 0?
Oh, you mean here?
Yeah.
Well, remember the top side, the normal point's in the j hat direction. Isn't j hat parallel to j?
Oh, and that yes equals 1.
Yes. Yeah. Because
Okay.
theta is 0.
Alrighty. And that 2 and the 0 given in the bottom and top integral for the normal top and normal bottom are just given to you, right?
I'm sorry, say that again.
The 0 and 2 on the top and bottom integral are given to you because you're given the dimensions of the box.
Yes.
Alrighty, thank you.
Right, the box is 2 by 2 by 2, right? And so
Yes.
this is in the y equals 2 plane, and this is in the y equals 0 plane.
All right, thank you.
Okay. Yeah, and I had this issue with the other group. One of the things you do have to remember the dot product, and you do have to remember the cross product. When we do magnetism, everything we do is going to involve cross products. So oops. Let me fix my slides here. Okay. So we can use Gauss's law to determine the electric fields due to a system of charges or a distribution of charges when we have a system that has a lot of symmetry. So let's write down Gauss's law. And now you're going to see the usefulness of Gauss's law. And the rest of the class is me doing examples. Okay, we'll write this down. The integral of E dot n dA is Q over epsilon naught. This is Q enclosed. This is whatever charge is enclosed inside the surface. If I can pull this dot product out of the integral this way, and I know what this dot product is, if I end up knowing what this dot product is, then that integral's easy over an area. I can solve for E, because if I know this and know this integral, I can solve for E. Okay? Of course, in order for me to be able to do this, I have to have a charge distribution that has a nice symmetry, and I have to be smart in choosing the shape of the box, the shape of the surface for which I'm going to integrate over. Okay? If I do a bad job choosing my surface, then I'm in trouble. I cannot perform the integral, and I can't use Gauss's law to calculate the field. And again, just as a reminder, Gauss's law is always valid. Okay? It's an always valid. It's a it's an important idea in physics. It's just that it is useful when you have systems that have a high degree of symmetry, because then you can pull the E dot n out and you can solve for E. And those are the problems we're going to look at now. Okay? Those are the problems we're going to look at now. Now, it turns out there's a certain set of conditions that'll help us in this endeavor. First of all, we got to consider this dot product. Okay. First of all, well, actually before that, the electric field has to be symmetric over the surface. It has to have the same value over the surface. I'll give you an example. Suppose here's a point charge, Q. You all know that the field is this. The magnitude of the field is given by that expression. If I draw an imaginary sphere around the charge, isn't it true that anywhere on the surface of the sphere, the electric field has the same value? Furthermore, the electric field is parallel to the normal to the surface. Everywhere around the sphere. That allows me to pull the E dot N out. And so by symmetry, we need to have E, the electric field, to be uniform over the entire imaginary surface I draw. If I do something crazy and I pick a box for my surface, then this dot product is not going to be constant over that whole box. Because if I draw my field lines, I mean, just look at this distance compared to this distance. They're different. So the electric field here is going to be different than the electric field here. And the direction's different. So this dot product will be different all the way around the box. I cannot pull this out of the integral. You can't pull, because it's not a constant. The choosing a box for that system is a really bad idea. And it turns out that this dot product has to be either E or minus E. In other words, these two vectors, in order for you to be able to pull this out of the integral sign, these two vectors have to be either parallel or anti-parallel to each other, so that the flux is E times A or minus E times A. Okay. Meaning the field has to be either parallel to the normal or anti-parallel to the normal. Same direction or opposite directions. And then the other case you can consider is that the electric field can be argued to be zero over the surface, which you can do that in some cases. So if I meet these conditions, I don't want to show that video, then I can calculate the electric field. And so I'm going to spend some time now using Gauss's law to calculate electric fields for various geometries. So I'm going to start with the following. I'm going to have a spherical shell. I mean, a shell is hollow, right? Or right at the bottom. So let's say we have a hollow sphere. It's an insulator, and it's isolated from the rest of the world, the rest of the universe. Okay, it's just a hollow sphere. There's nothing else in the universe. Okay? Because if I have other charges in the universe, then I have to look at the contribution to the total electric field due to all the other charges. Let's just say we have this thing here. Its charge is Q. I want to find a field inside and outside this thing. The radius of this we'll call B. I want to find the field inside this thing and outside this thing. And you might have done something like this with gravity. I don't know. So I'm going to draw an imaginary surface inside my sphere. And I'm going to use something that has the same symmetry as a sphere. So I'm going to draw a sphere. I'm going to draw an imaginary surface. It's in purple, of radius r. And the reason why I use small r because I want to find the field at some arbitrary location r inside the sphere. And I want to calculate this integral inside the sphere. I know there's no charge inside here, and I know there's no charge outside here because that's how the problem stated. Okay, this thing is isolated, and this thing is insulated. Okay? If there's no charge in here, then this integral is 0. Okay. Now I know there's no charge at all inside there. There's no dipole in there. There's just nothing in there. And I know there's nothing on the outside. So if this integral is 0, what can I say about the electric field then? From a physical point of view, what must the electric field be?
0.
0. It's 0 inside. Okay? So we can say that E equals 0. And oh, by the way, I shouldn't put an arrowhead here. See, the Gauss's law allows me to calculate the magnitude of the field. Gauss's law allows me to figure out the electric field strength, but not the direction. I mean, you have to use some physical intuition to get the direction. Okay? So I should write either this, or I should write it just like that. And that's true for R less than B. Now, what if I want to go out here? I want to find the field out here. Well, then I draw a Gaussian surface. I'm going to choose a sphere. I know this Gaussian surface, I know this charge is going to produce a symmetric field, like so. Because when you're outside the sphere, it acts like a point charge because of its symmetry. And so this integral is not going to be 0. It's going to be Q over epsilon naught because we're given the amount of charge on this sphere, so it's Q over epsilon naught. The question is now, how do I do this integral? Well, E, the red is E. The normal to the surface is parallel to E. That's true all the way around this thing. So E dot n is just E. And so now I just got to find the surface area of a sphere. What's the surface area of a sphere? Well, it's 4 pi r squared. And so this integral becomes 4 pi r squared times E. I solve for E. I get Q over 4 pi epsilon naught r squared. So then I get E there's a discontinuity there because there's charge on the surface of the sphere. And so if I graph the electric field as a function of position, it's going to be 0 up to the surface, and then there's a discontinuity. This is an open circle. Looks like that. And this should be make sense because it acts like a point charge. Okay. And so this is the easiest example you can do. Now let's make the examples a little bit harder. Instead of doing a hollow sphere, let's do a solid one. Not only that, let's make the charge distribution a little more complicated. Let me draw a solid sphere. And also the charge distribution is not uniform. Okay? Let's let rho be equal to some constant a over r. Let's let the radius of this thing be capital R. So the charge distribution is non-uniform, so this is going to help us to go back to homework problem number 9 on the previous assignment. I want to calculate the field everywhere inside and outside this thing. So I'm going to pick my Gaussian surface as a sphere like this. And what I need to do is figure out how much charge is enclosed inside this imaginary sphere, right? This term is whatever charge is enclosed inside this imaginary sphere. And so let's apply Gauss's law. And again, the electric field inside the, on this sphere is going to look like this. And all the way around is going to be parallel to the normal. So and it's going to be the same value. I can pull this out of the integral. We'll figure this out later. So this is going to be E times the surface area of this little purple sphere. Now I got to figure out how much stuff is inside here. How much charge is enclosed inside this Gaussian surface. Well, this is not a uniform charge density, so I have to do the following. I got to say, oh, this is equal to 1 over epsilon naught times the integral of rho dV. How do you break up a sphere into volume elements? Well, because the charge density only depends on R, then I can break the sphere up into a bunch of layers, like layers of an onion. And so dV is 4 pi r squared dr. And so I'm going to write E times 4 pi r squared equals 1 over epsilon naught times the integral of the density like that. What are my integration limits? Well, I have to integrate over this whole sphere, so it goes from 0 to whatever r is. And now I run into a problem. Your math professor won't like this because I've labeled r, I have the same label here as I do here, so somehow I got to make them look different. I got to make this look like a limit, but this look like a variable. And so a lot of times we define something called a dummy variable. And this is just for keeping track of everything, nothing else. I'm going to call these R primes so that I don't get mixed up between this variable and this number. So let's continue doing our integration. I'm going to pull out some constants. And that's an easy integral to do. Let's do it over here. So 4 pi cancels, right? Oh, and r squares cancels. And so what am I left with? I'm left with the fact that E equals A over 2 epsilon naught. So okay, now if I know what the total charge is on the whole sphere, I can solve for A, and then when you write the expression, it'll have a K and a Q in it. It'll have a form like Coulomb's law. Well, what do you notice about the field inside? The field inside is uniform. It's constant. That's just a constant. A is a constant, epsilon naught is a constant. The field inside is a constant. And in fact, the field inside is always going to be 1 power higher than the density. The reason why is because the electric field depends on 1 over r squared, but the total charge depends on r cubed. So the field inside is going to be always 1 power higher than the density. The field inside. Okay? So this is 1 over r, 1 power higher, which gives you a constant. So the field inside is constant. What about outside? Well, if I want to do this outside, let me redraw this. Then I got to choose a spherical Gaussian surface out here. Of radius r, arbitrary radius r. Everything proceeds the same way. Everything proceeds the same way. You're going to get this expression, this expression, this expression, and then you get to here. There's only one thing you have to change here, and I don't have to do the dummy variables here. What am I integrating over if I'm finding the field out here? Well, I'm trying to find the charge enclosed inside this sphere of radius big R, and so my limit here changes to big R. This changes to big R. This changes to big R. And that stays here. Okay. So then what's left? I'm going to be left with and so what can we write for the field inside? it'll just be in terms of that. Let me just catch up on my notes here. And so here we're going to write that. And notice when little r equals big R, I get that expression. That's because there's no charge on the surface. There's no surface charge density. Okay? And by the way, if you knew that the total charge was Q, you can solve for A. And when you do that, you substitute this in, you'll just get KQ over R squared. You have to do that. You have to get that because when you're outside, that sphere looks like a point charge. So that's a good exercise for you to try. You should do that at home. In fact, I expect you to do that at home, okay? Because you might see a problem like this on the exam. Because I do ask problems like this on the exam, okay? Let me do another example, different geometry. This time, we have, instead of a sphere that's charged, we have a line of charge. So here's a rod. Charge per unit length lambda. I want to first determine what the electric field looks like. Okay, I'm going to assume that this thing is infinitely long. Because if it's not infinitely long, the system is not going to have the geometry I need to apply Gauss's law. Just imagine this as being a bunch of point charges that are real close together. And the field lines are going to go like this eventually. So field lines are going to look like this. They're going to point away from the charge if lambda is positive. The question is, what shape should I use for my Gaussian surface, for my imaginary surface? I cannot use a sphere. That would be a horrendous choice. Because if I draw a sphere, and the field lines are doing this, then there's no way in the world I could pull the E dot n out of the integral. And so that's going to render, I won't be able to solve for E. It's too hard. I want to pick a better surface than a sphere. What would be a good surface I should choose? Well, you see it in the picture. Okay, I would choose a cylinder. Why do I choose a cylinder? Well, look. The normal to the surface of the cylinder is like this. Imagine drawing this 3D. If I have a line of charge, the electric field is going to point this way, and it's going to depend on R. So at any location on this cylinder, the field has the same value, points in the same direction as the normal to the surface. And so I can pull this out of the integral sign. What about the ends of it? What about the end caps of my cylinder? There's no field lines going through the end caps. And so I don't have to worry about the surface area of the ends. I only need the lateral surface area of the cylinder. Okay? So if this were a cylinder, I'm only considering this surface area, not the ends. Okay? Because there's no field lines that go through the ends. And so this is going to be easy for me. E dot n is constant over the surface. the lateral surface area of a cylinder is 2 pi RL. But the problem is L is infinite. Well, what about Q enclosed? Isn't Q enclosed infinite? Well, it's going to be, if this is uniform, it's going to be lambda times L. What happens to my L's? Well, they cancel. And so the electric field is lambda over 2 pi epsilon naught R. Or you can write it as 2k lambda over R, where lambda is the charge per unit length. Okay, that's the electric field due to a wire, a long wire. You might say, well, what use is it because it's infinitely long? There's no such thing as something infinitely long. We don't deal with that in real life. However, we can use this as an approximation to a field. Imagine you are really close to this wire. You want to determine the field at this point. If you're standing there, how long does the wire look? How does it look? Doesn't it look infinitely long? The answer is yes. And so, to a really good approximation, you can write your expression for the field is going to look like this. This is way faster than calculating the electric field using the methods we did in the previous chapter. So this is a great approximation. You'd probably be over 95% accurate. If you can afford 5%, if you can afford to be 5% off, then you can use that expression. The problem when you have a finite length wire is the field lines bend at the end, and some of the field lines are going to go through the cylinder. That makes the problem a lot more complicated. That's why we have to have the wire be long, okay, so that no field lines go through the end here. So there's no effect on the edges. By the way, I can do the same. I can use the same surface if instead of a wire I had, and that's a wire with no thickness, okay? But let's say I had a wire with thickness, a cylinder. I would be able to find the field inside and outside the cylinder in the same manner as I did the previous problem. The problem with the sphere, the only difference is I'm going to have to use cylindrical geometry as opposed to the spheres. That's something for you to practice on. Okay? These problems you have to know inside and out. Let me do one last one. It's a plane. It's a bunch of these rods put together, forming a plane, an infinite plane, a very large plane. Because it's hard, I can't draw an infinite plane, just like I can't draw an infinite line. But I'm going to draw a side view of the plane. Let's pretend it's positively charged. In the field, if this is infinitely large, the field will be uniform and it will look like this. Okay, I don't want to draw all of them. Okay? The field will be uniform, and a point like that away from it because it's positively charged. It's a plane, so really this is infinitesimally thin, okay? But I had to give it some thickness so I can draw it. It's positively charged. What shape should I use to calculate the electric field? I can't use a sphere. Sphere would mess me up bad. But you know what I can use? I can still use a cylinder. I can use a cylinder, and it doesn't have to be long. These field lines are going to go through the ends of the cylinder, parallel to the electric field. Of course, so if I draw my, let me get my container. So here's a cylinder. The field lines are going to penetrate this end and this end. Now, of course, the area of this cylinder, cross-sectional area, is going to be huge. It's got to match the cross-sectional area of the cylinder. Infinity, okay? We're looking at the limit as A goes to infinity. So this area and this area are the same. I can't make this infinitely big, okay, on a board. But let's assume that this area and this area are the same. And you have field lines going only through the ends. No field lines go through here. Okay, no field lines go around here. They go through this end and this end. That's it. And this dot product, again, is the same. So I can pull this out of the integral sign. And so I get E times the integral of dA is Q enclosed over epsilon naught. But there's two areas, one here and one here. And the normals are always parallel to the electric field. So these are always parallel to each other. These are always parallel to each other. Even though these both point in the negative direction, these two vectors are parallel to each other. So the two add up together. So we're going to have E times A, whatever this area is, plus E times A. So this is 2E times A. What's Q enclosed? Well, Q enclosed is whatever charge is enclosed inside my cylinder. This cylinder doesn't have to be infinitely long. The cross section has to be infinitely large. This can be short. And a lot of times it's called a pillbox. In the old days, that's what we would call it. The charge enclosed is going to be the charge density sigma times the area. The areas cancel. Those infinities cancel. Nice. And so E ends up being sigma over 2 epsilon naught. So that's what the magnitude of the electric field here is, and that's what the magnitude of the electric field here is. On this side, it points to the right. On this side, it points to the left. That's it. That's the field due to a plane. Yeah, there's no such thing as an infinite plane. However, if you have a disk and you find a field real close to the disk, it's approximately equal to this expression. I did a video calculating the field to a disk using the methods of chapter 23. If you either make the disk huge or you get real close to the disk, in the limit, you will get this for the expression for the electric field. Again, you want to prove that to yourself. You shouldn't have me show it to you every time. There's one thing you should try to do is try to prove these statements I'm making to yourself. Okay? That's how you learn the material. Go ahead.
I was wondering, why did you use sigma? Where did you get sigma from?
Well, I mean, if you remember from the chapter 23 homework, when we use lambda for charge per unit length, sigma for charge per unit area, and rho for charge per unit volume.
Oh, okay.
So this is an
more
area.
sense.
It's two dimensional. That's what we have been using. Okay. Any other questions? And yeah, and that's going to be a standard that we'll use for a two-dimensional object. We'll use sigma. For a three-dimensional object, we'll use rho, and a one-dimensional object, we'll use lambda. That'll be a standard, at least we'll use in this class. Okay? And most books use that standard. Okay, so study those examples. and try to prove those statements I made on your own. Okay? Now I want to say a couple more things about the material in this chapter. I was going to have a demo to show you, but the demo doesn't work very well. It was very disappointing when I did it yesterday. So if I can get it to work better, my Van de Graaff, I have a Van de Graaff here that I was going to use. It's not working very well. I want to say something about stability of systems under the influence of Coulomb forces. If you have a system of charges under the influence of Coulomb forces and it's in equilibrium, it turns out that the equilibrium is unstable. What does that mean, stable and unstable? Let's go back to Physics 205. Imagine you have an object at the top of a hill. It's just sitting there. I want to know if it's stable, without being rigorous, I want to know if the equilibrium point here is stable or not. If I give it a nudge to the left or to the right, what's going to happen to that object?
It'll fall down.
It'll roll down the hill. So that equilibrium is not stable, right? It's going to go in one direction or the other, depending on which way you perturb it. Now, what if I have that ball at the bottom of a hill, where the potential energy is minimized? If I push it to the left, if I push it to the right, there's going to be a force on it to the left, making it want to go back towards the equilibrium position. If I push this to the left, there will be a force on it to the right, making it want to go to the equilibrium position. It's called a restorative force. That equilibrium is stable because either way I push it, it wants to go back to the equilibrium position. That's a stable equilibrium. And you can use methods of Calc 1 that show that this is stable by showing that the potential energy is a minimum. Stable equilibrium means the potential energy is a minimum. Okay. If you have a system under the influence of electric forces only, and it's in equilibrium, that equilibrium is not stable. Okay, and it's really hard to prove that in this class, but if you take a junior level class, you can. Okay. I mean, really one of the ways is and you see in the picture there, if I move that charge from the equilibrium position, there has to be a restorative force towards the equilibrium position. That would mean that there has to be a charge there. That violates Gauss's law. There's a really nice way to prove it when you take a junior level course. So there's no such thing as stable equilibrium for particles in electrostatic fields. You can get a charged particle in equilibrium in a static field, but that equilibrium won't be stable. Okay? So that's all I want to say for that. I want to look at conductors in equilibrium. What does this mean? If you have a conductor in equilibrium, what does that imply? What does that tell us? Conductors are a different animal. And the reason why is because the electrons are free to move in a conductor. So to understand conductors in equilibrium requires some careful thinking. So let me draw a conductor of some arbitrary shape. And this has electrons in it that are free to move anywhere. If that conductor is in equilibrium, none of these charges can experience a force. Remember, F is Q times E. The conduction in equilibrium, the force on all the electrons and any one of the electrons has to be zero. that must mean that this has to be 0. So if you have a conductor in its equilibrium, the electric field inside has to be 0 everywhere inside the conductor. Otherwise, the charges are going to experience a force. They're going to want to move. So by definition, if F is 0, E has to be 0 inside the conductor. Now, having said that, we can then use Gauss's law or some other ideas to look at some of the properties of conductors in equilibrium. For example, if I charge this conductor, what's going to happen is the charge will rearrange itself so that it ends up on the surface. I can prove that with Gauss's law. First of all, if this is an equilibrium, and I draw a Gaussian surface here, E is going to be 0 inside. Okay? E has to be 0 everywhere inside here. So that this integral has to be 0. No matter what. And the only way to satisfy that in any case is that this has to be 0 inside here. And you can make this Gaussian surface bigger and bigger and bigger until you get to the surface. Once you get outside the surface, the field doesn't have to be 0, but inside it has to be 0. So all the charge has to be on the outside of the surface. The electric field on the surface of the conductor must always be perpendicular to the conductor. So let's charge this thing. We put all the charge on the surface. All the charge will actually go on the surface. That's going to result in the electric field that points perpendicular to the surface. It always has to be, it's always perpendicular to the surface of a conductor. It has to be. Why? Well, imagine the electric field pointed this way. That would mean it would have a component pointing perpendicular to the surface and a component pointing tangent to the surface. Well, if you have a component pointing tangent to the surface, then these charges are going to want to move in the direction or against the direction of the field. That would mean that this is not 0. Okay. Furthermore, we can actually calculate the electric field at the surface by applying Gauss's law. I'm going to use my pillbox. And I'm going to use Gauss's law. I'm going to apply Gauss's law on this thing. There's a field coming out of here. There's no field here. And so you have the integral of E dot n dA. I only have something coming through this surface. So the electric field ends up being sigma over epsilon naught. Locally, right? This sigma doesn't have to be the same all the way around, but it's going to have this value. And the last thing is, this value is maximized at sharp points in my conductor. So if I have a conductor that looks like this, the charge density is going to be higher here than here if this thing is charged. And that's the reason why is because charges can't move here very well, whereas they can move easily here. They can spread out very easily here. They can't there. So you can have a larger charge density here and hence a larger field there. Of course, I'm using a hand-waving argument to say that, but I have a better argument in the next chapter if we have time to do it. Okay. If you take a conductor and you put in an external field, the charges will distribute themselves until the sum of the forces equals 0. And when it does that, it's creating an electric field inside the conductor that cancels out the external field so that the total field is 0. And it does it in around 10 to the minus 16 seconds. Okay. All right, these next slides I'm going over, were basically the proofs of these statements. Okay, so let me go on. Okay, these slides that I'm going over are just proofs of the statements I just made. I was trying to get through the material before the class ends. Okay. What I want to do is I want to show you a couple of slides. Let me blow this up. These are two conductors in oil. They're the same. And again, I should credit the textbook. These are two conductors in oil. And there's threads in there. They're charged. The thread forms the field lines. Look at the field lines inside the ring. There's none. The field lines you see are between the conductors. That's it. Oops. Let me show you another example. Two conductors, again in oil with threads. Look at where the field lines are most dense. They're most dense near the sharpest point. And that's because the charges at the sharpest point have a hard time moving around, so they get bunched up there. On Monday, I'm going to do this problem. This kind of will summarize everything in the chapter. Okay, so I'm hoping that, so this will give you some time to let this information sink in. So I will do another example on Monday, and then I'm going to start chapter 25. Questions or concerns? Well, I'm glad the visuals help. I need those because I have a hard time drawing them. Thank you. No concerns, no questions. So you will see Professor Shakel on Friday. And I'm not going to, remember the office hours, the help hours tomorrow are canceled. Okay, because I'm going to be gone. I apologize for that. Just sometimes things come up. Okay. So I will see you all on Monday. Have a good weekend.
Thank you, Professor.
Thank you, Professor, for the lab.
I'm sorry? There was a question there about the lab. Okay, well, we'll see you on Monday then.